on this video we'll be starting a series wherein we'll be creating our own microkernel based operating system. Okay, so this will be a both design and implementation based, you could say, a series. So here we'll also look at the theoretical aspect as well as the practical aspects of developing your own operating system and how developing an operating system might help you in your programming career. So this will be just an operating system that we'll be creating which is for study purpose or like academic purposes. Okay, so it is not a commercial use of the shelf product like you could say Linux, Windows or Mac OS, that sort of a thing. But again, we'll draw the parallels whenever necessary with those products. Okay, and that might help you understand the topic better. Okay, so here we'll look at the general microkernel OS architecture, or what exactly is a microkernel. Okay, so for those who are not aware of the microkernel thing, so kernel is basically the operating system, or you could say the interaction between the real hardware and the application programs that we run on the computer. So that is basically the kernel. So what all things could be included in the kernel and what all things could be excluded from the kernel decide whether that kernel is a microkernel based implementation or a monolith implementation. So most of the operating systems, commercial operating systems that we use today, are monolithic based systems. Okay, so Linux, Windows, Mac and all those things definitely have the core philosophy of monolith based architecture. And like few RTOS, like real-time operating systems like QNX and all those things, they have basically a microkernel based architecture. So what is the distinguishing factor between these two systems is the size of the kernel basically. So here in a microkernel we use, or we have only the necessary services for building an operating system within the kernel. Okay, and other things are in the user space. So there are two parts basically. So one is the user space. So this part you can say this part is the user space, and from here this part is your operating system in case of a microkernel. Okay, so here you would see that we have implemented, or you can say we have designed for now only the necessary parts of interaction. Okay, so virtual memory manager or address space management. Okay, so this is a very important aspect, that is why it is kept in the kernel. Okay, so we have multiple processes and we have to allocate memory for it. So like multiple programs are running and context is being switched between them. So all things related to the process management are implemented in the kernel layer. So here you could see the virtual memory management, then there's a scheduler which takes care of context switching policy like the page replacement policy or like the scheduling policy or that sort of a thing is a part of the microkernel. And then finally the most important what you can say the module within a microkernel is the IPC, or the inter-process communication core, which takes care of message passing basically. Okay, so in a microkernel the most important aspect is the IPC. Okay, because that is the only layer, or you could say the only functional part that interacts with the user space, or in between the different user programs as well. They communicate via IPC only. There are no like ways to handle communication between this, like what you call different processes on a microkernel based architecture. So IPC plays a very important role. Okay, so the use of IPC in itself is important so as to avoid problems like race conditions while accessing hardware and all those aspects. So definitely this is one important module that we'll be seeing in the upcoming videos whenever we reach to that point of time. Okay, and these are the, like, let me just give you a gist of like how development will work. So hardware layers, basically your board will be there, like you have like system that you have. So we'll be developing on x86 based operating system. So x86 based CPU. So x86 is a very popular architecture, or you could say the most popular architecture by Intel. Okay, so we'll be using x86 architecture for our this thing we call the development part. Then there's a memory peripheral, so everything that comes within the board. Okay, so that is your hardware layer, and to access those things on the hardware layer, we usually have something called as a hardware abstraction layer, which is composed of partly assembly directives. Okay, so like assembly level programs are there, and also C programming. Okay, and that forms like a hardware abstraction layer where you have abstracted like the supported parts or the board functions, you can say. So like the BSP and all those things that you could add as something into an abstraction layer. Okay, so that will abstract the hardware for you and provide you a interface for easy access. Okay, so that falls into a hardware abstraction layer, the hell. Then after that you have the memory manager, like the virtual memory manager. So like on your RAM, okay, so if you're having a 4 GB RAM or 8 GB RAM, so like you do not allocate the complete RAM to a single process. So there are multiple processes running, like every process has its own address space. Okay, so that address space, but everything or the whole program is usually not loaded. It is loaded into overlays, or small parts are loaded, and those also are switched. So how that complete mechanism takes place is what is comprised into the virtual memory manager or the address space management. And then we have the scheduler, which is the process scheduler. Okay, so that will take care of the scheduling. So in terms of generalized architecture or generalized operating systems, you usually have a fair scheduler, like completely fair scheduler, and all those things are there. And in terms of RTOS and other things, you have like a different level of scheduler. Okay, so like priority based scheduling is there. Then there's like, you could say, round robin, like priority based round robin, or that sort of a thing is there. So complete this thing, like the whole scheduling is handled over here. So usually this is a very important decision, okay, when you develop your own operating system, like whether you want something or your operating system to be preemptible or non-preemptible. Okay, and when it should preempt or when it shouldn't, and how it should, okay, and how it shouldn't. Okay, so all these aspects are there. Then like I said, the IPC, that is the, like I will like to reiterate that part, like is the most important aspect over here. So that is there. And after that, in this section, your microkernel layer here. So here we could have very small services like clock, which are rather important, but like you could have it like at a higher layer, but at the boundary of it. And we could have a few other like non-essential but like gelling kind of things into this layer. Okay, so that completes this microkernel layer. And after that, there's a IPC layer over here as well. So like these things, the user processes communicate with the kernel via IPC mechanism over here. So there's very less use of what you call kernel calls as such. Okay, so that is also an important aspect. So you could do it in two ways. Okay, usually we have something called as a trap instruction, which transfers the execution to the kernel. Okay, so that is one way to do it. And other times we could do is like we could use an IPC based mechanism to communicate with the kernel, and then kernel will take care of things. Because here in this case we do not really require a trap instruction, because when you're using microkernel, okay, specifically microkernel, your device drivers, file system, and networking, all those things are a part of your user space only. So you need not worry about making trap instruction calls. Okay, so your kernel is slightly lighter on the side. So that way what happens is like the advantage of this aspect is like even if your drivers of one thing fail, Okay, so you say like some kind of like you could say disk drivers are failing or that sort of a thing, then your whole program, or you could say the whole operating system, is now rendered useless. So only that specific module gets what you call flagged down, or it is not working. And in that case also, in the runtime, if you can detect, you can have a monitoring service which could be running in the user space itself, that could take care of restarting that kind of a service. So you have like different types of monitoring tools also, if you come from a DevOps background, so like that take care of the liveliness of a certain application, and based on whether the state is live or not, you could turn them on, off, or that sort of a thing. So that could be done in a microkernel. But in case of a monolith, if something fails, then that is a death sentence for the kernel, and that is a root cause of something called as kernel panic. Okay, so when the kernel panic happens, usually people do a reboot, complete reboot, and some services fail. So there are things like busybox implementations or that sort of a thing, which will give you a minimal shell. Okay, from that minimal shell, you could do some kernel patching or that sort of a thing, and fix your kernel. Okay, so that is how it's done in a monolith way. But in microservices way, you could simply restart those driver level services and see if that is working, or if there is some inherent issue with the hardware, you could diagnose that as well separately. Okay, and on top of this user space libraries, you usually have this system libraries, like different types of C based libraries, other OS API implementations of that sort of things. So like all sorts of like standardization parts. Okay, so those exist in the system libraries or API layer. Okay, and finally the topmost layer is your shell user programs or GUIs or that sort of utilities and all those things. So everything in the topmost layer. So usually most of the interactions when we do application level programming are limited to the first two layers, like the application layer, and if you are into slight low level programming, then you might use C libraries, or you could say C++ related stuff, and that's the end of it. After that, you don't really interact with the low level things. Okay, but when it comes to OS development, you will have to interact with the low level hardware. So that is why it is important to understand, or you could say have an understanding of the hardware. Okay, so if you are developing for x86, now that we have seen the x86 architecture, so we should have a know-how of the x86 architecture, how the assembly works and stuff. Okay, and in the upcoming videos we'll see how we can cross compile, or you could say we could create our own architecture, cross compile it, or you could say cross compile and build our kernel. Okay, and how we can install, or you could say run that kernel into something like a emulator or a virtual machine like QEMU. Okay, or KVM or that sort of thing. We'll see how we'll do it. As of now, I haven't planned that far, but yeah, surely it would be a great start, and we'll see. It will be a great journey. Thank you.